In this video, we're going to study the definition of the integral. We will first look at a geometric inspiration for the definition, and then we're going to give the formal definition. So imagine that we have here function f, and we have the graph y equals f of x, and I want to look at the area under this curve between points A and B. So the area of this shaded region. We would say that the integral from a to b of f of x dx is the area of the shaded region. This is not a definition, but this is going to be a very good inspiration for us. You see, computing the area of this shape is very difficult. I don't know how to do it. But what I'm going to do is I'm going to approximate this area by using shapes that I really know very well how to compute their area. So, for example, the rectangle is very easy. We really know how to compute the area of the rectangle. It's just the width times the height. So I'm going to first have a rectangle that is entirely contained in my shaded region. So the area of the shaded region is definitely bigger than or equal to the area of this rectangle, which is given by m, which is the height, times b minus a, which is the width of my rectangle. Good. But now I can also overestimate the area by a rectangle that entirely contains my shaded region. So if the height is big M and the width is again b minus a, then I know that the area of the yellow rectangle is just m times b minus a. And then the area of my shaded region is in between the area of the pink rectangle and the yellow rectangle. Okay. Here we are underestimating and overestimating the area, but this approximation is not very good. The difference between my shaded region and the areas of the pink and the yellow rectangle is huge. They're not very closely related. So the idea here is that I'm going to split this region and now approximate it with rectangles that are entirely contained within this region. So here you see we have all these pink rectangles. They're underestimating the area again, but they better approximate the area of my shaded region. And I can do the same with yellow rectangles that are containing my entire region, but the approximation is again better. So then the area of my region, the integral between a and b of f of x dx, is going to be in between the area of the pink rectangles and the area of the yellow rectangles. Okay, but now what happens if I subdivide the region even further? As you can see, we're approximating the area even better. And then I can cut it into more pieces and get better approximation and even better approximation. So that would be the idea here. We're going to approximate the area of a region by using rectangles, and we're going to underestimate and overestimate that area. And by cutting our region in better ways, or cutting it into more little pieces, we're going to get better and better approximations. And that would be the inspiration for the definition of the integral. So the first step that we did was cutting the region into slices. And this corresponds to the notion of partition. A partition of the interval AB is a set P such that P is finite, P is entirely contained in the interval AB, and A and B both belong to P. So, when we write that P is equal to the set x0, x1, xn, what we mean here is that x0 is A, and then x1 is bigger than x0, x2 will be bigger than x1, and so on, and that xn is equal to b. So what we're saying here is that I'm writing the elements of my partition in increasing order, and that the first element is a and the last element is b. And here I'm giving you some examples of partitions of the interval 0, 2. So the most boring partition ever is the one that only contains the endpoints 0 and 2. But then we can have this one that gives points 0, 0.5, 1, 1.5, and 2. They don't have to be regular. Here we had the points spaced out every 0.5 unit, but it doesn't have to be. Like, for example, P3 is 0, 0.8, 1.3, 1.7, and 2. As long as we take a set with a finite number of elements. We make sure that all the elements are contained in the interval 0, 2, and that we have point 0 and the point 2 in that set. That would be a partition. Okay, so now the next step would be under and overestimating the area using rectangles. So what is the area of these pink rectangles? Well, we're going to compute the area of each pink rectangle here, and then we have to add it. So what is the area of the first pink rectangle? If you look at it, the height is just given by the infimum of the function on the interval from x0 to x1. Here you would say, why not the minimum? In this picture in particular, m1 corresponds to the minimum, but in general, we are not guaranteed to have a minimum. So that is why we need to use the infimum. Okay, so m1 is the infimum of f on that set. So then the area of this rectangle is the height, which is m1, times the width, which is x1 minus x0. Good. Now we need to compute the area of the second rectangle. So its height is going to be, again, the infimum of the function on that subinterval, the interval from x1 to x2. And the width is going to be just x2 minus x1. Now we repeat the same operation for all these rectangles and we add the area. So that gives me the sum from I equals 1 to 4 of m sub I times xi minus 1, where m sub I is the infimum of the function on the interval that goes from xi minus 1 to xi. Okay, now we need to overestimate the area using rectangles. In this case, we're going to look at these yellow rectangles that overshoot the area. So to do that, then what would be the height of the first rectangle? Well, that would be the supremum of the function on the first interval, and we're going to repeat the same operation for all the subintervals. So we get that this big M sub I will be the supremum of the function f on the interval that goes from xi minus 1 to xi. So if I want to sum the areas of all these yellow rectangles, we end up with the sum from I equals 1 to n of big M sub I times xi minus 1. Good. So now we have a way to underestimate the area with rectangles, overestimate the area with rectangles. Now let's make it formal. So we're going to define what's called the lower and upper sum. So we have a function f that is bounded on the interval ab, and we pick a partition p of that interval. For each I from 1 to n, we're going to define little m sub I to be the infimum of f on the interval from xi minus 1 to xi, and big M sub I is going to be the supremum of the function on the interval from xi minus 1 to xi. And then delta xi would be just the width of those subintervals, so it's going to be just xi minus 1. Then we define the p lower sum to be the sum from 1 to n of little mi times delta xi, and the upper sum would be the sum from I equals 1 to n of big mi delta xi. So the lower sum is the area of the smaller rectangles, this one that were pink in our case, and the upper sum is the area of the rectangles that are overestimating the area. In our case, those were the yellow rectangles. Good. So now the final step would be defining the integral. So the integral from a to b of f of x dx is a number, and this number will have to be between lower sum and the upper sum for any partition p that I pick. Because remember, the idea of the lower sum was to underestimate the area, and the idea of the upper sum was to overestimate the area. So this makes sense. Now, before I finish defining the integral, I'll give you some properties of lower and upper sum without a proof, and we're going to prove all those ideas that I'm going to give you next in the next video. So for now, keep watching, and I will prove the results about lower and upper sums, as I said, in the next video. So the first lemma here is that every lower sum is less than or equal to every upper sum, even if they come from different partitions. And this makes sense intuitively, because if you think about it, lower sums underestimate the area and upper sums overestimate the area. So therefore, any lower sum should be less than or equal to any upper sum that I pick. But as I said, we're going to prove this in next video. Now, here we have an approximation of the area using rectangles. If I get a better partition, then you see the sums of the areas of these rectangles is bigger and it gets closer to the true area that I'm looking for. If you get an even better partition, I get even closer. And again, the sum of the areas of these pink rectangles is getting bigger. So what happens here is that if I pick better partitions, the lower sums get bigger. And the opposite happens for the upper sums. If I get better partitions, the upper sums get smaller. So in a way, the best partitions would be the ones that give me the smallest upper sum and the largest lower sums. But the thing is that, well, the set of the lower sums might not have a maximum. So we'll settle for the supremum. And the same thing would happen with the set of upper sums. It might not have a minimum. We'll settle for the infimum. And that will give us the definition of the lower and the upper integral. So a function that is bounded, and I look at the set of all the partitions of the interval AB, the lower integral of f from a to b we're going to denote like this. It looks like the integral from a to b of f with a little bar underneath. So the lower integral would be the supremum of the lower sums of all the partitions of the interval AB. And then the upper integral of f from a to b, which is denoted by the integral from a to b with a bar above, is the infimum of all the upper sums. Okay, so we have this, and then as a theorem we're going to have that the lower integral is always less than or equal to the upper integral, and we're going to prove that in next video. But now we have this. So we're going to say then that a function is integrable if the lower integral is equal to the upper integral. And then the integral from a to b of f of x dx is going to be equal to, well, the lower and the upper sum, because they're both the same. Now, if we have that the lower and the upper integral are not equal to each other, which would mean that the lower integral is strictly less than the upper integral, then the function is not integrable and the integral from a to b of f of x dx is not defined.